How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is your first section of Chapter 19, Acid-Base Theories. So the first guy we're going to talk about is Arrhenius, and so we're going to talk about Arrhenius acids and bases. So acids are typically sour. Think about lemon juice. Their aqueous acid solutions are strong or weak electrolytes. They will cause an indicator to change color, and many metals react with aqueous acids to form hydrogen gas. Bases, on the other hand, are bitter. Think if you've ever tasted cocoa powder, you might think it would be sweet like chocolate, but it's actually very bitter. Bases have a slippy feel, example soap, and they will also cause an indicator to change. And aqueous base solutions are also strong or weak electrolytes. In 1877, Swedish chemist Svante Arrhenius, according to Arrhenius, acids are hydrogen-containing compounds that ionize to yield hydrogen ions in solution. Bases are compounds that ionize to yield hydroxide ions in aqueous solutions. Acids vary in the number of hydrogens they contain that can form hydrogen ions. A hydrogen ion or a hydrogen atom that can form a hydrogen ion is described as ionizable. Nitric acid has one ionizable hydrogen. Nitric acid is classified as a monoprotic acid, mono meaning one. Acids that contain two ionizable hydrogens, such as sulfuric acid, H2SO4, are called diprotic acids. Not all compounds that contain hydrogen are acids. Only a hydrogen that is bonded to a very electronegative element can be released as an ion. Such bonds are highly polar. When a compound that contains such bonds dissolves in water, it releases the hydrogen ions. Take, for example, hydrochloric acid. So we have HCl. We place that into water. It dissociates into H plus ions and Cl minus ions. In an aqueous solution, hydrogen ions are not present. Instead, the hydrogen ions actually join water molecules as hydronium ions. A hydronium ion is H3O plus, is the ion that forms when a water molecule gains a hydrogen ion. So when we add HCl to water, the hydrogen from the HCl actually joins a water, giving it H3O plus, or the hydronium, and then the chloride ion is alone by itself. Methane, or CH4, is a hydrogen-containing compound that is not an acid due to its weakly polar bonds. Acetic acid, HC2H3O2, contains hydrogens that do not ionize and hydrogen that does ionize. The hydrogen that does ionize is this hydrogen right here, because this is a very polar bond. These three hydrogens, however, do not ionize because they are nonpolar. Let's talk about Arrhenius bases, and the four most common that we're going to want to know are sodium hydroxide, potassium hydroxide, calcium hydroxide, and magnesium hydroxide. The base sodium hydroxide is known as lye, which is very caustic. A caustic substance can burn or eat away materials with which it comes in contact. This property is the reason that sodium hydroxide is a major component of products that are used to clean clogged drains. Group 1A, which includes potassium, reacts very violently with water, producing aqueous solutions of hydroxide and hydrogen gas. Calcium hydroxide and magnesium hydroxide are compounds of group 2A metals. They're not very soluble in water, and they're always very dilute in solution. If you have ever heard of or maybe even taken, it's called milk of magnesia. It's just magnesium hydroxide, but that is just something you take if you have an upset stomach. It's basically liquid Tums. So another guy was Bronsted and Lowry. This was two scientists who came up with their own definitions of acids and bases. So sodium carbonate and ammonia act as bases when they form aqueous solutions. But neither of these compounds is a hydroxide-containing compound, so neither would be classified as a base according to Arrhenius. So according to Bronsted-Lowry theory, an acid is a hydrogen ion donor, and a base is a hydrogen ion acceptor. This theory includes all acids and bases of Arrhenius defined, as well as some others. When ammonia dissolves in water, hydrogen ions are transferred from the water to ammonia to form ammonium ions and hydroxide ions. Ammonia is a Bronsted-Lowry base because it accepts the hydrogen ions, while water is a Bronsted-Lowry acid because it donates its hydrogen ions. A conjugate acid is the ion or molecule formed when a base gains a hydrogen ion. A conjugate base is the ion or molecule that remains after an acid loses a hydrogen ion. A conjugate acid-base pair consists of two ions or molecules related by the loss or gain of the hydrogen ion. So basically what that means is NH3 is our base. So we're going to call that B, which makes water our acid. And we've talked about before how water can kind of be both an acid and a base. So when the NH3 gains a hydrogen, it's now its conjugate acid. So NH4 plus is the conjugate acid, and OH minus is a conjugate base. So NH3 and NH4 plus are the conjugate acid base pair, and H2O and OH minus are the acid and conjugate base pair. An amphoteric substance is a substance that can act as either an acid or a base is said to be amphoteric. If we look at this list here of some common acids and bases, we know that water appears on both sides as an acid and a base. Sometimes water accepts a hydrogen ion, and other times it donates a hydrogen ion. This depends on what the other reactant is. So if we look here, back at this equation we just looked at, it gives up a hydrogen ion, whereas in other reactions it's going to gain hydrogen ions. So water is considered to be amphoteric. According to Gilbert Lewis, so here we have another acid-base theory, an acid accepts a pair of electrons and a base donates a pair of electrons during a reaction. So a Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. A Lewis base is a substance that can donate the pair of electrons to form a covalent bond. The Lewis definitions include all of the Bronsted-Lowry acids, which we know also includes all of the Arrhenius acids. So this is just a more broad spectrum. So let's consider the reaction of H plus and OH minus. So we have H plus and we have OH minus. And we know that OH has its 3 lone pairs and it has a negative charge, while H plus has a positive charge. So according to the Bronsted-Lowry acid base theory, we know that hydrogen will donate itself to the OH and we will see water form. The other theory is that H plus and OH minus, again with its lone pairs, the OH donates its lone pair to the H plus. So since the H plus is accepting the electrons, it is the Lewis acid. So here we still have HOH, but this is the Lewis theory, and this one above is the Bronsted-Lowry theory. So they're very similar, it's just comes down to, is the hydrogen grabbing onto those electrons, or are those electrons being donated to the hydrogen? So in review, you can just copy down this little table. This will be a perfect little wrap up for you, something you'll want to memorize so you can identify these as Arrhenius, Bronsted-Lowry, or Lewis acids and bases. According to Arrhenius, acids are hydrogen-containing compounds that ionize to yield hydrogen ions in aqueous solution. Bases are compounds that ionize to yield hydroxide ions in aqueous solution. According to the Bronsted-Lowry theory, an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. According to Lewis, an acid accepts a pair of electrons and a base donates a pair of electrons. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, Resources CD, and PearsonChem.com. Have a great rest of your day.